Welcome to topic 5, in which we're going to finally look at the rotational absorption spectrum. So we've seen expressions for the quantized rotational energy and worked out the rotational term f of j, which is given by bj j plus 1, where j is the rotational quantum number and b is the rotational constant. And here the rotational term has units of centimetres to the minus 1. So that gives us an energy level. But spectroscopy considers transitions between levels. So we're going from one level to another level. So we need to calculate transition wave numbers, so the wave number difference between these two energy levels. But before we do that, we need to think about which transitions are allowed. And in order to work out which transitions are allowed, we need to consider the selection rules. So this is the first of many sets of selection rules that we're going to see as we go through this course. For most selection rules, there is a global selection rule and a specific selection rule. So here, the global selection rule, which states that the molecule must possess a permanent dipole moment. So if it doesn't possess a permanent dipole moment, we can forget completely about rotation absorption spectroscopy. If it does have a permanent dipole moment, then we can go and think about the specific selection rule. And the specific selection rule for rotation absorption spectroscopy is delta J is equal to plus or minus 1. So this says that in a transition from a certain J value, J can only go up or down by 1. And this has an effect on what the spectrum looks like. The reason why delta J is plus or minus 1 is because the molecule is interacting with a photon of light, and a photon has 1 unit of angular momentum. So this, as it interacts, as it's absorbed by the molecule, it can either increase the angular momentum of the system by 1, or if the angular momentum is pointing in the opposite direction, it can decrease the angular momentum of the system by 1. So these are the selection rules for rotation absorption spectroscopy. And we can now use them to work out what a rotation absorption spectrum looks like. So it helps if we build up a table. So here we have a table with J, so the rotational quantum number, and F of J, so the rotational term, which has units of centimetres to the minus 1, and we can just fill it up. So if you remember, F of J is equal to Bj, J plus 1, we can work out all these values in terms of B. So we have 2B, 6B, 12B, and so on. Now when you remember the specific selection rule, it says delta J is plus or minus 1. So if we start off in level J equals 0, from there we can only go to level J equals 1. And if we start off in level J equals 1, we can only go to J equals 2 or down to J equals 0. So we only need to consider the energy gaps between adjacent energy levels. So we can work those out. So 2B, 4B, 6B, and so on. And now these are the possible amounts of energy that the system can absorb. So if we were to plot these on a spectrum, we get a spectrum that looks like this. So we have transition wave number across the bottom with units of centimetres to the minus 1, intensity up the y-axis, and we'll get a peak at 2B, so that's this one here. We'll get a peak at 4B, so that's this one here. And so on. So we're getting a series of transitions. So this is telling us where the peaks are going to occur. We can now do the same thing algebraically. So the transition wave number, so nu tilde, is given by the rotational term of the final state minus the rotational term of the initial state. And this gives us 2b, j plus 1, with units of centimetres to the minus 1. So from this expression, we can see that we would expect to see a series of lines separated by 2b, because that's this number here. And if we go back to the previous slide, then that's what we've already expected to see. So the spectrum is going to look something like this. So the first peak is the transition j equals 0 to j equals 1, second peak j equals 1 to j equals 2, and so on. Putting the labels on these peaks is known as assignment. So here we've assigned all the peaks in this rotational spectrum. Again, here we're just looking at the position of the peaks. We've now got to move on and think about the intensity of these peaks. But that's for the next topic. So here's your homework to show that the transition wave number nu tilde is given by this expression here. And that's the end of this topic.